Welcome to the Toon Show. I'm your host, MC Toon. I love to have fun promoting science and critical thinking. Often I do this by debating against flat earthers, 5G nutters, and other science deniers on my YouTube channel, MC Toon Live. I also feature pre-recorded videos explaining science in an irreverent way on my Conspiracy Tunes channel. Jump on YouTube to see them and subscribe while you're there. You can search YouTube, or they are linked on my website at mctoon.net. Today, I have a Danny Faulkner. I'll just let him introduce himself. He will do a better job than I could. So take it away, Danny.
Thank you, Michael. By the way, you said you'd take on science deniers. There are people out there who call me a science denier, so be careful. Again, I'm an astronomer. I have my PhD in astronomy from Indiana University. And for more than a quarter century, I was on the faculty at the University of South Carolina, Lancaster. By the way, just before we started this recording, I had a student from over 25 years ago who happened to be at the museum, and we met and spent some time together today. That was really a pleasant surprise.
Oh, that's nice.
So I had an opportunity about a decade ago to retire a little bit early, and that allowed me to come up to Northern Kentucky to join the staff at Answers in Genesis. We run the Creation Museum and our Ark Encounter, both theme parks or attractions here in Northern Kentucky. And I'm on the research staff as a staff astronomer. I run some of the programs we do. And I also do a lot of writing and some speaking. Since I've been at AIG, I've written about 6 books, and also have written numerous articles for our website. I have about 30 articles and or blogs on our website that deal with flat Earth. So if people want to see what I've written, they can certainly go to our website, which is answersingenesis.org, and just search for flat Earth, and it'll bring up all my articles. And about 5 years ago now, I think it was 2019, so it's been about 4 years ago, I collected some of my articles together, edited them heavily, and added a lot more, and published this book, Falling Flat. And it's there you go, thank you. And it has like 370 pages in it. So I meant it to be a rather extensive coverage of it. And I get accused all the time. I go out there on the Discord servers for flat, like FE 24/7. And the first thing they ask me, are you researching, writing another book? They keep accusing me of writing another book. No, I'm not writing another book. I won't say I'll never write another book on flat Earth, but I think I did a pretty definitive treatment, and I just can't imagine why I would write a second one on it. But I do continue to write and critique on this.
Good. Well, the reason why this particular topic came up is because I did a video on my Conspiracy Tunes channel where I accidentally conflated parallax and stellar aberration. And in the comments, a bunch of people pointed that out. I said, hey, I will have to get myself up to speed on that. And I asked you specifically if you would do a little presentation on the topic so that everybody can, myself particularly, can know the difference between them. And so that's why we're here.
Okay, be happy to do this. They are related in the sense that they're caused by the same sort of thing, our orbit around the sun. Aberration is due to our motion as we orbit the sun, and parallax is due to our changing position due to our orbit around the sun. And of course, as you well know, the relationship between velocity and speed is velocity is the time derivative or the time rate of change of position. So that's why they're related. Before I jump into it, I probably ought to talk a little bit about coordinate systems we use in the sky, because I will be referring to one of those. And if I don't define that, it might be a problem. And anytime you want to navigate on a sphere, like, say, the globe Earth, and yes, it is a globe, you generally use, on the globe at least, latitude and longitude. And you start these systems, these coordinate systems, by having a reference circle. In the case of the Earth, it's the equator. And it's important that that circle be what's called a great circle on the sphere. Probably people know from geometry that if you intersect a sphere with a plane, you will get a circle. The intersection of the two will be a circle. But there will be various sizes of circles. But if you have a one that goes, the plane passes through the center of the sphere, then you will get the greatest diameter and greatest circumference. That will be equal to the diameter and circumference of the sphere itself. So we want to start with a great circle arc, or great circle, and the great circle we're going to talk about on the Earth at least is the equator. And then you have meridians. By the way, when you get that great circle of your reference circle, then you automatically have 2 poles, one up here and one down here. Imagine that plane that intersects the surface of the sphere and passes through the center of the sphere. Suppose that you made a line perpendicular to the plane, and it's at the center of the sphere. Then it's going to poke up here and down here in those two poles. And you use the poles and this circle, great circle, as a reference. If you're at the center of the Earth, then latitude would be the angle that a position would make with respect to the equator of the Earth. So you go from 0 to 90 north and 0 to 90 south, complete 180-degree realm. And then you have meridians of longitude going like this. They too are great circle arcs. They run really only halfway around from pole to pole. And since they're equivalent, all of them are the same as any other, you pick one to be your reference. And the one we generally pick on the Earth is Greenwich over here. That's the prime meridian. You measure either east or west of that, or one way all the way around. That's something everybody should have learned in grade school. All right. Now, when you get into the sky, I know of at least 4 different reference ways of measuring coordinates. One of them is what is generally called the horizon system. Now, Austin Whitsitt recently stumbled across this on, I think, Stellarium, and there they called it the horizon, no, it was called the azimuthal grid system. Azimuth grid system. I never heard it called that before. I've heard it called the horizon system, and I kind of took him to task a little bit and for calling it that until somebody pointed out to me that Stellarium calls it that. I don't know why they do, but you have the same thing. You have, first of all, you got to realize that the sky appears as a celestial sphere. The ancient Greeks taught that this was actually what was going on. You had a tiny little Earth in the middle and this large celestial sphere. I think Ptolemy placed the radius of this thing like 10 or 20,000 times that of the Earth. And the stars and the sun and the moon and the planets were all on that celestial sphere. Now, the flat earthers see this, and they only see the half that's above the horizon. You have a horizon right here. And so you see one half of that, and they think that is the a literal dome over top of the Earth. But, the whole thing spins like this. Either it spins or we spins. It really makes no difference. And as it does that, you can have part of it above and part of it below. That's why we know there's a sphere here. So we take the horizon as being our reference point, our reference circle. Automatically, there's a pole up here we call the zenith. There's one down below we call the nadir. So you got meridians of azimuth running from pole to pole, from zenith to nadir. And you have parallels of altitude running like this. And so it's like latitude and longitude on the Earth, except we call them altitude and we call them azimuth. As with longitude on the Earth, all the meridians of azimuth are equivalent. They're all great circles, circle arcs. So we pick the one going through the north direction to be our reference, and we go eastward 360 degrees. So something that's due east, it's 90 degrees azimuth, 180 degrees south, and then 270 west, and so forth. And you can measure altitude and azimuth. And this system is useful in navigation because you use a sextant and you measure rapidly 2 stars, measure their azimuth in the sky, record the time. It's not the azimuth, the altitude. And then I would do it by solving a couple of spherical triangles on the surface. But the way navigation is generally done, they make up a little way of doing it. Similar thing, but done differently. In mathematics and in physics and so forth, you encounter more than one way of doing something, even though you're really doing the same thing. And that's how navigation works. You tie it to a fixed coordinate system in the sky because this horizon system is fitted just for your location, date, and time. Now, just as the Earth has an equator, we can have a celestial equator in the sky right here. And it's just simply a projection of the Earth's equator out into space. You take the poles and you stretch those out. Remember that line perpendicular to the plane that defines the equator would intersect the sky in the north celestial pole and the south celestial pole. And this is the system around which the sky seems to appear every day, seems to spin every day. In reality, I think the Earth is spinning, but for our purposes, it doesn't matter if we're spinning west to east or if the whole sky is spinning east to west, you get the same result. Now, you have the celestial equator here, and so you can have parallels of declination, how far north or south you are of the celestial equator. You also pick a prime meridian of right ascension in the sky. It's the one that passes through the vernal equinox. So it's just like analogous to what we do on the Earth. Now, I said all that to get to this. The sun each year seems to follow a path in the sky we call the ecliptic. And I can do this with a celestial sphere. If I can hold it up high enough, I can move this little yellow ball around, and that swings throughout the year. And notice that it doesn't quite follow the celestial equator. Over here, the sun is in June, and it's well north of the celestial equator. But in December, it is well south of the celestial equator. That's because the Earth's axis of rotation is tilted 23.4 degrees. And since the axis of rotation is perpendicular to that plane that it has there, then the equator, the ecliptic, that's the plane of the Earth's orbit around the sun, it has to be tilted 23.4 degrees to the celestial equator. Now, there is a ecliptic pole, and it's 23.4 degrees away from the north and south celestial poles, those two north and south ecliptic poles. You've heard of precession of the equinoxes. The north celestial pole actually swings around in a 25,600 to 900 year cycle around the ecliptic poles. All right. Set all of that to finally set up what we can talk about aberration and starlight and parallax. Any questions so far, Mike?
I'm good so far. I'll just say that some people may be listening to the audio only podcast version of this. If you want to see what he was pointing to, you can find it on the Toon Show on YouTube. But hopefully your imagination was able to fill in some of the details.
If you didn't follow all of that, that's fine. I will be talking about the ecliptic later on, and I wanted to set that down. So it just, well, I have to find that before or after, and I'd rather do it beforehand. So, all right. Now, parallax is apparent shift in position due to our revolution around the sun. And the way I demonstrate this for people, I have done this for years, I have people hold their thumb out at arm's length like this. And if you look at one eye and then look at the other eye, your thumb seems to shift with respect to distant objects. And so thumb seems to do that. In reality, it doesn't do that. Your eye is simply changing the position. And how much that angle changes, the position changes, depends on two things. It depends on how big your baseline is, how far apart your pupils are, and also how far away it is, how long my arm is like this. The farther away it is, the smaller the shift. The larger my baseline is, the smaller the shift. So there's a relationship there. And this parallax effect has been known for thousands of years, and it is a principle used in surveying. For instance, if you wanted to measure the distance to some distant location, like a rise, a hill or a mountaintop, you could start from where you are and just take a chain and go length to length to length, which is the most direct way to do it, probably the way that most flat earthers would think you would have to measure these things. But you can do it smarter than that. You can take a theodolite and set it up here and look at that, measure the azimuth of that distant object, and then shift over maybe 20 or 30 feet with your theodolite and do it again. And you're going to end up with two positions, two different angles like that, just like looking at that thumb at arm's length. Knowing your baseline and knowing the angle that you've measured, you can then use trigonometry to measure that distance. It would be the sine or the tangent that you would use, but since these angles tend to be very small, we can get away with what we call the small angle approximation. And that works up to about 15 degrees within 1%. If you get down to less than a degree, it's much, much better than that. And all you do there is you take the angle will be equal to the baseline divided by the distance, and the angle has to be measured in radian measure. That's something you probably learned in high school or college math. I wrestled with it a long time until I finally figured out this is really a more natural way of doing it than doing it in degrees and so forth. All right, so the ancient astronomers realized that if the Earth orbited the sun every year, if the heliocentric theory were true, then they should see parallax. You see, the ancient astronomers, mostly were geocentrists, but they considered the heliocentric model, and they reasoned that if you orbit around the sun, the sun's right here, and one side of the Earth's orbit's your eyeball here, and one's over here, then the stars should shift back and forth. And they diligently searched for it and never found it. So if you're a good scientist, what are you going to conclude? You're going to conclude that you've disproved the heliocentric theory and you become a geocentrist. And that really was the issue that separated people back then. There were a few people, such as Aristarchus, who believed in the heliocentric theory for a couple of reasons. And when challenged with how do you explain the lack of parallax, they said, well, maybe the stars are incredibly far away, which indeed turns out to be the case. And by the way, the reason why Ptolemy set the size of the celestial sphere around 10 or 20,000 times that of the Earth, he realized that diurnal parallax, that is, as the Earth spun every day, would cause an apparent shift. And he didn't see that. So he reasoned that if the sphere were that large, 10 to 20,000 times out of the Earth's radius, then you wouldn't see diurnal parallax.
So he estimated the kind of the minimum size based on the lack of measurable diurnal parallax.
Yeah, that's daily parallax due to the Earth's rotation. So
interesting way that he got that.
Did some good science, actually. Not bad at all. If he would have applied the same reasoning for the heliocentric model, he might have turned into a heliocentrist at that point, but he didn't. And the same logic really applied. Well, by 1600, people had begun to abandon the heliocentric model. Certainly in 1600, most people in Europe were geocentrists. In 1700, hardly anybody was. There was a tremendous change that took place during that time. It was basically based upon rejection of the Ptolemaic model. When Galileo saw phases of Venus, that disproved that at least Venus. It showed that Venus did not orbit the orbit of the sun had to, and that kind of unraveled all that. But also some of the other objections were removed by looking at Jupiter's satellites and so forth. So that was the real advantage of this. It's a simpler model once Kepler modified it with the elliptical orbits. But there was no direct evidence of the heliocentric model for another 100 years or more, and that was interesting. What they wanted to look for was parallax, and they looked and didn't see it. Let me talk about parallax here for just a minute, because again, if you orbit around the sun, the stars should shift back and forth. Let's suppose that the sun is get something here to work with. I'll just grab this styrofoam ball here. Let's suppose that this represents the sun, and if I'm on the Earth here and I'm orbiting around the sun like this, the plane of my orbit is going to be in the horizontal plane right here. And let's suppose we have a star up above me here, the ceiling of my office here. That would be near the north ecliptic pole. And so if I'm on this side of the Earth, of the sun, I would have to tilt my telescope this direction to see it. And 6 months later, I'd have to tilt it the other direction. So it'd be a shift, one side looking this way, one side looking that way to make that point towards the star. It's going to be a very narrow angle, but it's going to be an angle. Notice the direction I'm pointing it. I'm pointing toward the sun. Here I'm pointing towards the sun. Over here, I'm pointing toward the sun. When I'm over here, I'm pointing it toward the sun. And over here, I'm pointing it toward the sun. So if I do that over a whole year, pointing toward the sun, toward the sun, toward the sun, when I finished, I would end up with a little circle that it would make in the sky. That would be its parallactic circle in that sky. And you're going to measure this with respect to background stars. The problem is which stars are background, which stars aren't. That's a problem. One way they selected stars for study, because parallax studies traditionally have been very labor intensive. It takes a lot of effort to do one star. So what they looked for were stars that had large proper motion. Proper motions were noted probably about 300 years ago or more, because they were able to compare modern measurements of stellar positions and compare them to ancient records. For instance, Sirius, the brightest star in the sky, it's remarkably in a slightly different position from how Ptolemy recorded it 2,000 years ago. So by 1780s, 1790s, 1800, they were regularly measuring proper motions. They'd measure positions of stars, come back 10, 20 years later and compare them. William Herschel, very famous astronomer from the end of the 18th century to the beginning of the 19th century, he measured proper motions of actually dozens, if not hundreds of stars. And from that, they had if a star is really close to you, it's likely to have a large proper motion. Moving across the sky is what I'm saying by proper motion. Yeah. From one generation to the next, it doesn't mount much, but over many years, you can see it. And so if a star is nearby, it's likely to have a large proper motion. If a star is far away, it's likely to have a small proper motion. So that's one way to sort out the nearby stars. Just look for large proper motion stars. So it is a little tricky until you get your bearings about you. Then suddenly the system starts to make a lot of sense. But the important point is you got a little circle if a star is near the ecliptic pole. Now, what if it's not? What if the star is in the ecliptic like this? If that's the case, and if I'm looking at a star right towards you in the screen, then I'm going to point it this direction, again towards the sun. And over here, I'm going to point it again towards the sun. But when I'm over here, it's going to be pointed that way. And over here, it's going to be pointed that way towards the sun. So you're not going to get a circle like you would at the ecliptic pole. When you're in the ecliptic, it's going to be a line going back and forth like this. That's a parallactic line. Well, if that's at 0 degrees ecliptic latitude, and a circle is at 90 degrees ecliptic latitude, then in between, you're going to get an ellipse.
Yeah.
And that ellipse is going to be, its long axis is going to be parallel to the plane of the ecliptic. And how elliptical it is, how much it's been tilted, depends on your ecliptic latitude. And again, involves one of the trig functions of that. So when they make these measurements, they know which way the orientation is. And when they measure over the course of generally 6 months apart, they can do it throughout the year, should find a little bitty ellipse coming out of that. Does that make sense so far?
It does.
Yeah.
Yeah. And of course, you would, some of them you can't see because the sun's in the way part of the year. So you'd have to choose your time based on its location, based on where the Earth is in relation to the sun.
Yeah. What you would do is you would want to maximize it. So you would generally do it 6 months apart. You would do one at generally around sunset when the star's high in the sky. And then 6 months later, you do it at sunrise when the star is still high in the sky. Yeah. And so you don't really need to get the whole ellipse. You just simply need to get the extremes of that because you know what the location will be in between.
Yeah.
Now, the first measurements of parallax were in the 1830s. Several people did it nearly simultaneously. Bessel was the first. He did a star called 61 Cygni, which had one of the largest proper motions in the sky. Somebody else did Alpha Centauri, I think, and a few other stars. So that came all in the 1830s, and we've been building upon that ever since. You had classical techniques that really were at their peak probably around 1900. And then there was a revival back about 30 years ago when the European Space Agency launched the Hipparcos mission. It was a satellite to orbit around the Earth. And it extended out the distances we could get parallaxes up to that point. You had about 20% accuracy out to about 60 light years. That's it. And Hipparcos shoved it up to about 600 light years. And more recently, the Gaia probe has shoved it out to about 6,000 light years. So now we have pretty good parallaxes for millions of stars within 6,000 light years. And that's really remarkable. We've been able to do that. And there have been some improvements on the ground too, by the way.
For reference, we can only see with our eyes a certain distance, certain brightness stars. How does that compare to the 6,000 light years?
Most of the stars you see at night are a few hundred or a few thousand light years. One of the most distant, easily recognizable stars is Deneb. It's one of my favorite stars. We think it's around 3,000 light years. We don't have a good parallax measurement on it because it's too bright to be recorded in the Gaia catalog, unfortunately. The stars of Orion are like 400 to 600 light years away from us. So there might be a few stars out there that are pushing that 6,000 light year limit, but for the most part, they're all within that limit.
So with a few exceptions, the stars that we can see have generally had their parallax measured.
Yes. Now with Gaia, most of the stars we can see. The brightest ones perhaps not, but because the Gaia spacecraft just simply cannot measure terribly bright stars. It's kind of, you have to max out where you want to have the best sensitivity, and they would go with the millions of stars rather than a few hundred stars.
Yeah, so it's tuned to see the dimmer stars.
Yes, it is tuned.
Yeah. All right.
So, sorry. Make my apologies to the audience too. So Now, the first measurements of parallax were made in the 1830s, but there was a guy named James Bradley in the 1720s, 110 years before, who tried to do it. He was in England, and he had another fellow who worked on this. And they picked a star. They picked the star Gamma Draconis, I believe. And the reason why they picked that one was because it was a fairly bright star. It's the brightest star in this constellation Draco. And where he lived in England, it was nearly overhead. When it passed overhead, it was at the zenith for him. So he had a very good telescope maker build this very fine telescope, and they mounted it at the bottom of a chimney. I guess they weren't using the chimney anymore. Maybe they built it specifically for this. You've probably heard the story that from the bottom of a very tall chimney, you can see stars in the daytime. Well, you can see the brightest stars in the daytime, but you can't see most of the stars. But when you put a telescope on it, you can actually do that. You can see bright stars through some telescopes in the daytime, particularly if you're in down the bottom of a big tunnel, like that, a big tube. And so he could observe this thing every day and every night that was clear. And that was advantageous. And so they bolted this thing solidly to this, but they also had a little adjustment on it that they could turn these screws very finely tuned so they could tell how much they had to move the thing in order to keep a star centered. And you want to catch it as it's transiting. That means it reaches the highest point in its motion above you. And so they studied this, and right away, within a month or so, they started seeing a shift in the position of Gamma Draconis. And they thought at first that they were seeing parallax. But after about 3 months, they realized they had a problem going on here. Let me get back to my little demonstration. Here's the sun again. Remember, if I'm orbiting around, look at a star near the ecliptic pole. If I'm orbiting around and doing parallax, I'm going to kick my telescope toward the sun, like that. But if I'm doing, what he found is he went along like this. He wasn't tilting his telescope toward the sun. He was tilting his telescope 90 degrees from the sun, in the direction he was moving around the sun. So over here, instead of pointing this way, he was pointing that way. And over here, instead of pointing this way, he was pointing that way. So everywhere he was going,
so how much direction of motion? How much toward the, like a little toward the sun or zero toward the sun?
Well, the parallax is toward the sun. This is 90 degrees, so it's in the direction of our motion. It's along 90 degrees to it.
And this was in the 1700s, so they didn't
around 1724, I believe.
They didn't quite have the precision then to actually measure parallax.
Yeah, I skipped over this. The largest parallax of any star is Alpha Centauri, Proxima Centauri, and it's about 3/4 of an arcsecond.
Okay.
And for people, Michael, they don't teach seconds and minutes of arc in school anymore. It's all decimal. So for folks that are a little younger than we are, you take a degree, which is 1/360th of a circle, and you divide it into 60 minutes, and then each minute is divided into 60 seconds. And an arc minute or so is about the smallest angle that the human eye can detect without optical aid. So it's quite a bit smaller than we can see. And the 3/4 of an arcsecond is about the angular diameter of a dime at a couple of miles. So you can understand why the precision wasn't there yet in the instrumentation. It was another century later before they had that. But they didn't know. They didn't know how big parallax would be because they didn't know the distance to any of the stars. But when they did their experiment, they found that it was tilting 90 degrees off from what it should be. And it was a little over 20 arcseconds. So now we're talking about something that's, 40 times the largest parallax of any star. So it was detectable even in probably earlier than Bradley did in the 1720s. And it took them a while. They puzzled over it for a couple of years because they couldn't figure out what they were doing wrong, because they were looking for parallax, and they found something in the wrong direction. If you look at a star at the ecliptic pole, it's going to be a circle. And if you look at it in the ecliptic plane, it's going to be a back and forth line. In between it will be an ellipse. So Gamma Draconis was actually an ellipse that they saw, and they measured it throughout the year as an ellipse, but they realized the direction was not quite right. It was 90 degrees off from the other one. That's the relationship there. So it took them a couple of years to figure out what was going on, and they realized that it was an effect of the finite speed of light. And the analogy we use is if you're in a rainstorm, no wind is blowing and you're standing still, you can hold an umbrella like this and everything is fine. But if you start walking through the rain, if you hold it like this and I'm walking this direction, the rain is going to come in and hit the front of my body. So what you can do is tilt your umbrella forward like this, and as you walk forward, the rain is going to miss you pretty well. And so what he was doing is he was tilting his telescope forward about 20 arc seconds all the way around. And the understanding came a little later, and they had an idea what the speed of light was. And so when they knew the size of the Earth's orbit, they could figure out how much it ought to be, or from the measurement of how much the aberration of starlight was. And knowing the speed of light, they could figure out the size of the Earth's orbit. You can go either way with that, but it was consistent with what they knew, approximately the size of the Earth's orbit and the speed of light at that time. And it's again like 20.2 arc seconds. And the important thing is, it's the same for every star. That 20.2 is the same, but for parallax, it depends on the distance. It could be zero or essentially unmeasurable if it's far enough away. And so you've got these two different motions now. How do you sort through that if you're trying to make these measurements? Well, one's a systematic change, a shift that every star undergoes, and the other one is relative to that. It's an absolute shift, basically subtracting that out. So if you took a photograph, very high precision photograph of stars, they would all be subject to the same amount of aberration of starlight, and you wouldn't see any shift. But you would see on that photograph, that plate of that photograph, you would see annual changes in position due to parallax taking place.
Okay, so this in the 1700s, the speed of light wasn't well known yet, right? That wasn't until the 1800s really that it.
Well, they got it to like 300,000 kilometers per second by the 1850s. I think the first really good measurement was done by Couzeau, the guy with the toothed wheels. And that was like 1840, 1860. That was the way to do it. They had measured it before that. And the first measurement is accredited to Romer, though he really didn't calculate that. He simply demonstrated the speed of light was not infinite, which was debated at that time. Oh, yeah. But in the 1720s, I think they knew the speed of light probably within 10 or 20% of the correct value today.
Okay. So that was good enough for them to determine that the aberration was a factor they needed to consider.
Yeah.
Yeah, okay.
And it took them a year or two to figure that one out. Well, in retrospect, it's pretty obvious, but at the time it was brand new stuff and they didn't know what to do. And it's an interesting story. I was surprised to learn a number of years ago, I read about this in detail, that they were actually I knew they were looking for parallax, but I was not aware until I looked into it one time that they were rather puzzled for some time trying to figure. They realized they had a problem because it was in the wrong direction, off by 90 degrees.
Yeah. Interesting. So, and it's the relationship between the speed that the Earth is orbiting the sun and the speed of light.
Yes.
Together. So if our orbit was larger and moving faster linear speed, then the amount of aberration would be more.
Yeah.
Right.
So if you did this experiment on another planet, you would find that aberration of starlight would be different. On Venus, it's closer to the sun, so it orbits more quickly, and so the aberration of starlight probably close to 30 arc seconds. You go to Mars, it's probably going to be closer to 12 or 13, I would think.
Okay. That's very cool. So is there more, or is that?
That's basically it. I mean, we can keep talking. You can ask me questions if you'd like, but I know it's a lot of information to be digesting at once. It
certainly is.
And by the way, both of them are evidence that we do orbit the sun.
Yes.
And the flat earthers like to quote Einstein when he says, they come to the conclusion there's no way using optical means to measure the Earth's motion around the sun. But the problem is, what did he mean by optical means? And in the context, he was talking about interferometric measurements, like with a Michelson-Morley interferometer. And he obviously that's what he was talking about, but you have aberration of starlight and parallax, annual trigonometric parallax, which indicate very strongly the Earth is orbiting the sun. There are other methods of doing this. By the 1880s, they were taking spectra of stars, and there's a periodic Doppler shift in those. If a star lies near the ecliptic, then it's got about a 30 kilometer per second shift. It's blue shifted part of the year, and 6 months later it's red shifted, because on this side of the orbit you're moving towards the star, and this side you're moving away. So it's 30 in, 30 out. Now at the ecliptic pole it's 0. So again, you end up with things that are a trig function of that angle. And I used to do a lab exercise with my students where they would take some spectra of the star Arcturus, which is like 30 degrees out of the ecliptic, and you would measure its Doppler shift on one side of the orbit, and then 6 months later the other side of the orbit, then get a measurement of its speed, and you apply the correction. If the students were diligent about it, they got a value of our orbital speed to within 1 or 2% of the correct value. It's amazing how good that was. And my own work, I encountered this. I have something like Romer's work. When I do eclipsing binary stars, these are two stars that are orbiting around each other like this, and they're so close together and so far away from us that we can't see the individual stars, or light blends together to look like one star. But one star passes in front of the other each time. When that happens, you end up with an eclipse. So the light dims and then recovers and then dims again on the other side. And this is going to probably blow you and some of your mind and minds of some of your viewers. The stars that I study are pairs of stars that are comparable in size and temperature to the sun. You've got two sun-like stars here, and they're orbiting around typically between 8 and 15 hours.
Wow.
Yeah, so in one night, we can get one complete light curve in some cases.
How far away from each other are they?
They're almost touching. They're kind of egg-shaped, and there's matter slopping between them. And there's a lot of interesting astrophysical things going on. I've been doing this for 45 years. And as we do this, we can see evidence of mass transfer. We can see hot and dark spots. We see spots on stars like we have on the sun. So we know several different lines of evidence that there are spots on other stars as well.
So how do you determine that there are spots?
Well, what happens is, suppose there's a spot on this star right here, and it's going to be a little dimmer on this side. Then when you go over here, it's on the back side, you can't see it anymore.
Okay.
That shows up as an asymmetry in the light curve.
Yeah, when they're 180 degrees apart in their rotation around each other, and you see a little less brightness.
And then when the spot is on the spot side facing you, you'd see less light. On the other side, you don't see the spot, so it's a little brighter.
Yeah, so you're getting an average of all the spots.
Pardon?
So you're getting an average of all the spots, because there may be multiple.
Well, actually, we have a very sophisticated model we apply to it, and we can actually get kind of a region of spottedness we can actually do. It's not just all of it. We can actually, because it changes as the phase goes around like this, it changes. And so we can model where the spots are. It's amazing stuff we're able to do today with the high-speed computers. We can put those through. Marvelous model that was written, code that was written back in the 70s, but back then computer time was pretty expensive. Today it's pretty cheap. You can run them on a desktop now instead of a mainframe. And so we've been modeling these for years. But to get back to my point, is one thing we want to know is the period. And so we measure when the eclipse takes place. The light dims down and recovers, and we can typically measure that within about 8, 9, 10 seconds accuracy. And so what will happen is that if we're orbiting around the sun, if the stars say over here, the direction you are, when I'm on this side of the sun, I'm 8 minutes closer to it by light travel time than I am over here or over here. And that depends, again, if it's in the ecliptic or not. So if I don't correct my measured times of minimum light throughout the year, they will vary with an amplitude of 8 minutes times the cosine of the ecliptic latitude. So what we do is we always reduce our measured times of minimum light to what we call heliocentric times of minimum light. And that's what I publish as heliocentric. We want them sun-centered. What we measure is geocentric. And of course, if a flat earther here's out, going to say, well, see, you're admitting the Earth isn't moving. No, I'm admitting that I'm on the Earth, and I'm going to observe things on the Earth. It's geocentric in that sense, because that's where I live. But if I don't correct that, then another astronomer who wants to compare their observations to mine, they're going to have to make some sort of allowance for that. So I just simply correct mine to the sun all the time. And if you don't apply that, again, they will wobble up and down. But if you do correct it, they're flat and horizontal. So I have done direct observations of the fact that we're orbiting around the sun for 45 years. I've been encountering that since the late 70s.
So you can, with aberration, not just know that we are orbiting the sun, but actually output the velocity that we're moving around the sun.
Yes.
And you must take it into account for doing some other types of observations.
Yes.
That's something. That's very interesting. You're right. It is mind-blowing to think that there's two suns that close to each other and how quickly they orbit each other. The centrifugal forces involved must be quite something.
Their orbital motions are like 1,000 kilometers per second, or maybe probably a few thousand. The shortest period system I've done has been 6 hours. Done a few of those. So they're 4 times a day they're orbiting around each other.
And so how do you see these optically? Do you have a telescope that you own, or is this through some other?
I've used various telescopes over the years. When I was in grad school, I had exclusive use of the 16-inch Bowler and Chivens, which is an incredible telescope. I also made research trips to various places. I've been to Kitt Peak Observatory in Arizona, Lowell Observatory in Arizona many times. Been to Cerro Tololo in South America 4 times. I've used ones in North Carolina, Georgia, South Carolina, Indiana. So I've used and hope to use one of our telescopes here one day. I've been working on getting it up to standards. Michael, there are amateurs who do this kind of work. Believe it or not, it's one of those citizen scientist things, and we've relied upon amateurs for quite a bit over the years. But with this modern electronics, amateurs can do quality work that only professionals could have done a generation ago. So there are amateurs who actually do first level work for us.
Yeah, that's pretty cool that technology can shorten that gap between what the highest budgets can do and what somebody just as a hobby can do.
Yep.
Huh. So the other then is so Einstein specifically mentioned 2 things. One was aberration, the other was the red shift and blue shift. And you mentioned that in passing. Can you explain a little more on those 2 or on that one particular type of measurement or observation?
Yeah, if an object is moving, or we're moving with respect to it, doesn't matter. You're going to have some motion, Doppler motion showing up. And, the Doppler motion, the Doppler effect, most people have heard with sirens and horns of a vehicle is coming towards you, and then it goes past you. If it sounds a horn, it will go, like that. The Roadrunner cartoons and the coyote and the train, they always do that kind of stuff. And I remember as a kid doing this, I had this crazy bell on my the ding-a-ding-a-ding on my bicycle, and I would ride past one of my friends and going the other direction on their bicycle as fast as we could. You hear this ding-a-ding-a-ding-a-ding-a-ding-a-ding, it went by, and then we switched bicycles, and I could hear it as well. So everyone's experienced this. Well, light does the same thing. So again, if I'm on one side of the Earth and there's of the sun orbiting the sun, and there's a star off in this direction, here I'm moving toward it, and so it's going to cram those waves. The Doppler effect is going to cram the waves closer together, so it's a higher frequency of light. Or if I'm moving 6 months later, moving away, it's a lower frequency. Or I would say would be a shorter wavelength on one side and a longer wavelength on the other, because I tend to think in wavelengths more than frequencies. And the way that shows up in stars is you have in their atmospheres, the spectra of stars, it looks like a continuous spectrum with dark, what we call absorption lines running through them. This is something also flat earthers are pretty ignorant of, I do believe. The spectral lines we see in the stars are identical to those we see in the lab, or can create in the lab. And so we can put a sample in a spectrograph in the lab, and we can say, okay, this thing contains so much sulfur and so much potassium, and it's been standard procedure for 150 years to do this. And it's all under controlled conditions, true, but when you look at stars, and they started doing this in the 1880s probably, we see the same sort of absorption lines. In fact, a guy named Fraunhofer saw these over 200 years ago. Optically, visually, he saw them, but now we record them photographically. But these absorption lines are the same as the emission or absorption lines we can create in the laboratory as well. We can recreate the conditions in the laboratory that we see, same spectrum that we see in the stars. That's how we know what the sun is made out of, and how we know what stars are made out of. But if you watch very carefully, those spectral lines that look like they occur at certain wavelengths or frequencies, as they orbit around the sun, they shift back and forth like this. Shift shorter, longer over the course of a year. And if it's at the ecliptic poles, there is no periodic Doppler shift. Only in the ecliptic do you have the maximum 30 kilometers per second. As you increase your ecliptic latitude going towards the poles, it decreases and decreases and decreases. Again, that's what you expect if the Earth is orbiting around the sun. You could argue that the entire universe is orbiting around us once a year. That's the Tychonic people do that. Flat Earthers haven't gotten that far, I don't think. But so all you do is you measure the spectroscopy, and you measure those wavelengths, and then you can calculate the speed for yourself. And again, I taught this for 30 years. Had my astronomy students who actually would do a lab where they took a photograph. It was a lab produced by Sky and Telescope magazine years ago, but it was a nice little lab where you could take the photograph, work out the plate scale. You had to measure the plate scale, and then make your measurements, multiply by the plate scale, and then get your Doppler shift, put in the Doppler formula. And if the students did it right, they got done. They got around 29 to 31 kilometers per second, and 30.
So, for reference, what's a plate scale?
Oh, plate scale is how many, in the case of a photograph of spectrum, it would be how many angstroms there are per millimeter or per inches on the plate. If you're talking about a photograph, it might be how many arc seconds there would be per pixel or something like this. So it's simply relating some linear thing you're trying to measure in terms of the pixels or the actual measurement. If you have a photograph, just lay a ruler down. I do that sometimes when I'm trying to measure things dealing with flat Earth things. I make those kind of plate scales as well.
Okay.
It's called a plate scale because originally photographs were done on glass plates. We don't do that anymore.
Yeah, going back a long time ago.
Be careful.
Oh. Being careful. He is retrieving something from a cupboard or an office here.
Yeah, I have a few plates that I took.
Oh, cool.
Back in this would have been about 40 years ago. In fact, this one I'm holding up, I took it on June 26, 1981. So there you go.
42 years ago?
I keep everything. That's a glass plate, folks. That's what they look like. This is a small one. Most of them are bigger than this.
Is that a picture of stars, or is that spectral, or what is that?
To tell you the truth, it's garbage. But the equipment I was using wasn't the best for this. Actually, this is a photograph of the planet Uranus. What I did is I took Uranus over several nights. And then I could compare them. I could see the orbital motion of Uranus over several nights. I got one here, the moon, which is tricky, but can you make that out at all? The moon, it's a negative.
Oh, yeah, I can see that.
Yeah, so that was cool. I was using a 12-inch refractor, a refracting telescope with a 12-inch diameter lens. The focal length was about 15 feet. And it was a remarkable telescope. It really was. But the drive wasn't as good as it could be, and the lighting conditions, and I didn't know what I was doing. So okay. I would love to go back to that observatory and use modern digital cameras on it, because that thing would be an incredible thing for the planets.
Is that observatory still in existence?
It is. It's on the campus of Indiana University. Okay. And it was built in 1900. And it's a big brass thing, and they remodeled it about 20 years ago. I gave a little money to it, so I went to the rededication when they did it back in 2000, I think. But it's called Kirkwood Observatory. There was a famous astronomer there named Daniel Kirkwood. He discovered what's called the Kirkwood gaps in the asteroid belt. And so they named it for him.
Very cool. So here's a question. Why is it called Uranus and not Caelus?
The Caelus is, what was that from?
Well, all of the other planets are named after Roman gods.
And Uranus is not a Roman god?
Uranus is the Greek name for Caelus.
Ah, well, I don't know the answer to that. I did not know that. Is Neptune the Roman or Greek name?
Everything is Greek. I'm sorry, everything is Roman except
for Uranus. That's interesting.
Yeah, well, Uranus is the outlier. And of course, 13-year-old boys around the globe laugh at its name.
I know. We all do, actually, don't we? The the question is, the joke is, speaking of astronomy, what do you think of Uranus as a whole? So that's one of the ones. I'll let other people pronounce it the way they want to, but it's generally correctly pronounced Uranus, which kind of takes the fun out of it. I suppose
it removes some of the fun.
But Michael, it was controversial what to call it for many, many years. It took about 50 years to figure it out. When William Herschel discovered it in 1781, he wanted to name it Sidus Georgia, which is Latin for Georgia Star.
Oh, okay.
Because King George III, which we in the colonies rebelled against, was his king. And by just being the first man recorded in history to actually discover the planet, King George was pleased anyway. And he gave him a nice stipend for the rest of his life to continue his work and be available to show the royal family anything they wanted to at night, but that was on rare occasions. And he then became a world-class astronomer, and he wanted to call it George's Star. And of course, the French didn't want that at all, so they debated for many, many years. I had a colleague of mine at the university who was an English professor, and he had inherited a very nice library from his grandfather, I guess. And in it was a star chart or charts, a big chart from around 1840, shortly before the discovery of Neptune. This was 60 years after Herschel discovered Uranus. And on this chart, they had a chart of the solar system, and it was merely called Herschel.
Herschel.
Yeah, because they'd still not ironed out what to call it yet.
Because he was, wow.
And so they eventually said, look, since all the planets are named after Roman gods, let's continue that. But I did not know until you just told me a moment ago that Uranus is a Greek name. And now I'm going to have to go look that up and see why they didn't name it for Caelus, being the Roman name.
Yeah.
That's interesting.
I'm sure there's a 13-year-old boy in there somewhere in that story. So.
It could be. And they followed that with the discovery of the asteroids. The first four were discovered shortly after 1800, midway between Uranus and Neptune's discovery. So they named them Juno, Vesta, one of the other Ceres, Ceres, and then one other that's escaping me right now. Are those? Do you know if those are Greek or Roman? I think Ceres is Roman.
I can look it up here quick.
Yeah. Juno, Vesta, Ceres, and what's that fourth one?
Ceres is Roman.
Okay. Juno, Roman. That sounds Roman.
It does.
Doesn't sound Greek at all. And Vesta sounds Roman.
Yeah.
Juno, Vesta.
Yeah, Juno's Roman.
What's that fourth one? 4 asteroids.
I'm sure there's people listening along right now that are just yelling out the name.
Pallas, Pallas. Yeah, and that sounds Latin to me. So it's interesting that they.
Yep, it is. It looks like it. Yep.
Okay, so they. That's funny, and so I did not know. That is curious. I need to find out more about that.
There it is. Some homework left for the viewers. Why is it Uranus instead of Caelus?
Now, maybe I should start a program to rename it.
That's it. 13-year-old boys will be sad. Well, Danny, thank you for this. It's been really good information. I'm glad to be corrected when I make a mistake. So aberration is not parallax. They're distinct from each other. So anything else before we go and remind people how they can...
I want to thank you for having me on. It's been good to be back with you. We need to do a program again. Anytime you have a question you want me to elucidate upon from astronomy or physics, I'll be happy to come back with you.
Absolutely. I'll be sure to do that. I have a few more questions, and so I'll be tapping you for more of that in the future.
All right.
So, all right. Well, thank you for joining us today. If you would like to see this podcast as a video, or to have a conversation about it in the comment section, you can on YouTube, search for Toon Show. If you like the podcast and want to support it, you can head to patreon.com/MCToon. We'll see you next time.